Okay, so this time I'll talk about recurrent neural networks. I think a lot of this will be, if people are already familiar with recurrent neural networks, will be relatively easy. But it's something that's very important for neural networks for NLP. So I will go through it. I'll try to go through the easy parts relatively quickly. So if there are any questions, feel free to ask. And then maybe we can spend some more time on elaborating. Or I got a question about the stack RNNs on Piazza, and I can talk a little bit more about that as well. Okay, so let's go with the first one. So in NLP, we have lots of sequential data that we would like to handle, this could be words and sentences, or characters and words, or sentences in a discourse, etc. And all of these have kind of long distance dependencies in them in some way or another. And there's tons of these dependencies that span over long distances, but just to give a few, agreement and number or gender, etc. So this is an example that I also used in my my machine translation class. But if you have he does not have very much confidence in himself, it should be himself. And if it's she does not have very much confidence in herself. So this is an example of long distance agreement in gender. This doesn't happen very much in English, but it happens a whole lot in a lot of other languages in the world. Where you have to do this. So if you know Russian or another language like that, this is very important. Another example is selectional preference. This happens in basically every language in the world. So this is an example where we have a word that's pronounced the same but is spelled two different ways. So the reign has lasted as long as the life of the queen, while the rain has lasted as long as the life of the clouds. So you couldn't create an accurate speech recognition system that distinguished between these because they're pronounced the same in American English anyway, or my version of American English. And unless you looked at the very last word here. And there's lots of examples of this as well. Some other ones you can come up with kind of arbitrarily complicated cases. So what is the referent of it? This is an example of an AFRA resolution or co-reference resolution. So the trophy would not fit in the brown suitcase because it was too big. So what is it? Trophy. Very good. So the trophy would not fit in the brown suitcase because it was too small. So now what's it? Suitcase. Okay. Does anyone know what this is? There's a name for this. Yeah, very good. Winograd schema. So this is a famous thing that is trying to come up with difficult common sense reasoning things. And they're based on language, but they also require you to know that basically the trophy is going inside the suitcase. So if it's too big, then the thing that's going inside is the problem. If it's too small, then the thing it's going into is the problem. So you can take a look here. I've not actually downloaded this data and looked at it, but I've seen a few examples, and it looks pretty interesting. It might be fun to play with if you want. So one way to solve these kind of long distance dependencies in a generalized way is recurrent neural networks. So basically, you can think of them as tools to remember information over arbitrarily long time spans. And the feed-forward neural network looks like this. We do something like look up a word vector. We do some transform of it, and then we make a prediction. So, for example, in our feed-forward language model, our context would be the past 2 or 3 words, and then we'd run it through a neural network layer or something. And recurrent neural networks look like this. So basically what you do is instead of just taking the context, you take the previous prediction or the previous hidden state as well. And unrolling them in time looks like this. So One important thing to notice here is that this graph looks like it has a cycle in it. And when you have a cycle, you can't do backpropagation. And the reason why you can't do backpropagation, or well, at least you can't do it in the normal way, is because basically backpropagation is a dynamic programming algorithm that assumes that things are in topological order to do it properly. If you have a cycle, there's no topological order, so you couldn't do this. But fortunately, if you think about it over a whole sentence, basically you have your vectors that you looked up here. You take the hidden state at time 0, you do a transform with the RNN, get the hidden state at time 1, make a prediction. Do the transform at time 2, make your prediction, time 3 prediction, time 4 prediction. And if you get this far, now suddenly there's no cycles in the graph anymore, right? So it's just a normal directed acyclic graph, and we can train it like we can train any other neural network. So how do we train? We have maybe our predictions 1, 2, 3, 4. If we have labels 1, 2, 3, 4, like part of speech tags or whatever, then from these labels we can calculate a loss 1, a loss 2, loss 3, loss 4, and then basically add them all together. And now we have our sum, which is our final loss function. And then we can do backpropagation with respect to this. So this is just a graph where we calculate a loss function and do normal backpropagation. We could think of it as a big feed-forward neural network, basically, where it's feeding forward from the end of the sentence or the beginning of the sentence to the end of the sentence, and then from all the predictions into the loss function, et cetera. Any questions so far? No? Okay. So yeah, the unrolled graph is a well-formed directed acyclic graph. We can run backprop, so we take our total loss and we run backpropagation like this and pass stuff all the way back. Parameters are, so one important thing is that the parameters are tied across time and the derivatives are aggregated across all the time steps. And this is called backpropagation through time. Just to give an example of what we mean by this, basically, you can see that I have multiple RNN steps here, but the parameters for all of these RNN steps are the same, essentially, because we're doing the same transform at every time step, which means that if we do backprop, basically the gradients of these parameters will be the sum of the gradients that we get from all of our predictions. So that's good. The reason why it's called backpropagation through time is basically we might have our loss from over here in time step 4, and it kind of goes back through time step 4 to time step 3 to time step 2 to time step 1, etc. So it's going back through time. Okay, so that's the basics of RNNs. I think it's review for a lot of people, but are there any questions? No? Okay, I'll continue. So what can RNNs do? There was kind of a, there were 3 things in the materials. I actually prefer to think of them as a classification of 2 things. So one thing it can do is represent a sentence and use that representation to make a prediction. Or it can represent a context within a sentence. So it will read the context up into that point and use it to summarize the sentence, the context at that particular time step. In the reading materials, there was also a distinction between an acceptor and an encoder. I think basically these are kind of 2 instances of the first one. So both of them are calculating a representation of a sentence, and then how they use them downstream, either to make a single prediction about the sentence, yes or no, or for something more complicated, is basically the distinction between these 2 here. So in my mind, basically, number 1 and number 2 are the main distinctions of this. So let's say we want to represent a sentence. We get, I hate this movie, and then we can make a prediction. about the sentence here. Maybe this is our sentiment prediction. And this could be done for sentence classification, conditioned generation, so like translation or dialogue response generation, which we'll talk about later. Also retrieval, which I'll talk about in the next class. And if we want to represent contexts, we can predict particular labels from each of these. And we can do that for tagging, language modeling, calculating representations for parsing, etc. So if we're talking about language modeling is basically a tagging task where we want to tag the next word in the sentence. And the way we can do this is by basically taking the initial hidden state and inputting the beginning of sentence symbol, calculating a representation, and then predicting the word I. Then we input the previous word, do this, predict the word hate, and do this all the way to the end until we get the end of sentence symbol. So this is the same as our feed-forward network, except the big difference between this and our feed-forward network is now that we have this kind of recursive process in generating the representation. So this is one example. Are there any questions or stuff like this? No? So one thing maybe I should mention now, I'm actually going to talk about this more in detail later, but the problems that we encounter here in the representing sentences and here in the representing contexts are actually very different. In the representing sentences, task, we only have one prediction at the very end of the sentence, and this actually makes training RNNs very hard. The reason why it makes training RNNs very hard is basically we're passing information along lots of time steps, and we need to remember this information all the way through the sentence. Well, for representing contexts, it's actually not as hard at all because we get feedback from the label immediately after consuming a word. So if you hear about things like RNNs being hard to train, it's mainly in the first part, although in the second part it can be true as well. And I'll talk about this in a little bit more detail later. Okay. So any questions, clarification? Okay. Okay. So the next thing I will talk about are bidirectional RNNs. So bidirectional RNNs are a simple extension to this. Basically, the idea is that you want to do it in both directions. So you read from the end of the sentence, or from the beginning of the sentence all the way to the end of the sentence, and the end of the sentence all the way to the beginning of the sentence. And then based on this, you can concatenate these two representations and make a prediction of something like a part of speech tag like this. So the good thing about this is basically what you're doing is you're getting all the information on the left from your forward RNN, you're getting all the information on the right from your backward RNN, and then you're using this to make a prediction about the tag. So you're considering everything else in the sentence when you're making a prediction. Basically, I'm going to talk about LSTMs in a little bit, but basically a bidirectional LSTM for some sort of sequence labeling or something is an extremely strong baseline. It's extremely easy to make and works extremely well. So this is something that you definitely want to have in your arsenal if you're trying to do any sort of sequence labeling or something like this. And they're not too difficult to implement either. Just a very quick clarification. Can we use this for language modeling? Anybody?
Yes.
Yes?
Yes.
Anybody disagree? Anybody disagree and have a reason why? Yeah.
Well, you can't into the future.
Right, exactly, yeah. So the answer is no, and the reason why is because Language modeling is calculating the conditional probabilities of all of the words in the sentence. Sorry, I'll call this X. Up to I, let's say this is this. And we do this by decomposing. We calculate the probability of the first word, and then we calculate the probability of the second word given the first word, etc. If we use this for language modeling, then we will basically be conditioning on all the words when we predict the second word, and that's not allowed in language modeling. So if you're doing language modeling, you have to do left to right. If you're doing something like machine translation, also you need to generate the words in a particular order, so you have to go left to right. Other applications like tagging, where you're going to predict tags based on all the words in the sentence, it's fine to use this in both directions. Okay. Yeah.
But I mean, to get the context representation, one can still go in the reverse order from the last word, just to quickly
For language modeling, or for language modeling, you could model in the reverse order, or you could model in the forward order, but you can't really do both. And the reason why is because you need to predict these variables in some sort of sequence. You could also theoretically predict the word in the middle first, and then predict outward from there, or something like that. But you have to have a sequence where you predict one word first, then the next word next, and you can't use information about words that you haven't predicted yet. So it is important that you have some sort of ordering of the variables you're predicting. Yeah. Yeah.
Currently, therefore, a unidirectional RNN which models context cannot be used for a task like machine translation for the same reason?
So you can use it on the input. You can use it on the input side. So if you're translating from Chinese to English, you could use it on the Chinese side, and you always do, or not always, but often do. But on the English side, you need to generate words in some order, right? So again, you can only use them unidirectional. You could think of, so one example where you could use it is you could use it for rescoring. So if you have a whole bunch of hypotheses that you want to score for some reason, you could do that, but it wouldn't be a probability model. It'd just be like a scoring model or something. Yeah.
Would like left to right language modeling and right to left language modeling, would they be like significantly different or have different properties?
Yes, they would. They would have different properties. Theoretically, it makes no difference. So theoretically, if you decompose the probability in this order, or if you decompose the probability in the opposite order, it's still the joint equal to the joint probability. But because you have modeling errors, because our models are not perfect, you will have different characteristics based on the order you go in. And there was actually an interesting paper at EMNLP just a week ago, where basically they used a fancy strategy for generating output for neural MT systems, where they combined the two models together, and they got significantly better results when you combine one that goes from left to right and right to left, because they have kind of different biases, for example. So I think there's evidence that the biases that there definitely is a difference in the things you capture going from left to right to right to left, but that's only a function of modeling errors, basically. Interestingly, generating from right to left was much worse than generating from left to right. I don't know why, but it's good that left to right seems to make more sense to us as humans, and you got better accuracy as well. Sometimes that's not the case with neural networks, and something that makes no sense actually tends to work pretty well until you figure it out. So. Okay, cool. So we have. I'd like to try it out. I'll just talk a little bit about how we do this in DyNet, and I think this is similar to some toolkits. It's different to some other toolkits. But basically, in DyNet, we have a builder, a thing called a builder, which can be like an RNN builder or an LSTM builder. And what we do is we specify the number of layers, the size of the input, the size of the hidden layer, and in the model where we store the parameters. Then we can add parameters to the computation graph and get the hidden state per sentence by calling this initial state function. and then we update the state and access it to make predictions per input word or character or whatever. So yeah, this is parameter initialization. You can just look at the code, but then this is sentence initialization. So the most important thing here is that the word embeddings are word embeddings for each word here. Then we might start the sentence by adding the word embedding for the end of sentence symbol. And then basically what we can do is we can walk through the sentence. Every time we get the we do the s.output function to get the output of the recurrent neural network. Then we can calculate the loss for the next word, append this loss, and then add the next word like this. So basically, this is how we can create a language model. It's a for loop where each time we make our prediction, then we add the input for the last prediction we did. Then we can sum all our losses together. So this is an implementation of basically the graph that I showed earlier. So here we have something that's actually a little bit different from that. I just realized now that the order of our examples and slides was somewhat out of order, which is my fault. But I think Max will talk about how to do this for a different task, which is sentiment. And hang on a second, I will pull that up. So we have sentiment RNN. Okay.
Graham?
Yeah.
How could I do it in there? I don't know how to use Mac.
Oh, okay. How do you go up and down?
No, I mean, how could I make it larger?
Oh, make it larger. Make the screen larger is this, and then make the font larger. There's a weird shortcut that isn't working right now.
Command plus 6.
What's that?
Try command plus.
Command plus.
Uh,
Oh, there we go. Okay. Sorry, I was using the Vim shortcut on Safari, which doesn't help.
Okay, so this is the code. I think for this code, we do not have to have much to say because the central part of this code is just how could we construct the RNN. So where is this part? Here. So okay, the name of the variable is confusing. Here we only use RNN. We do not use LSTM. So I think we should change this to RNN. So here is we just use the simple RNN builder, and this is the input dimension. This is the dimension of the hidden state, and this is the model. And we use bidirectional, so we have the forward RNN and the backward RNN. And these are the parameters for the softmax layer. And here is how could we can calculate the scores. So basically, this is only the transduce, yeah. So we just get we first get the initial state of the RNN, and we use the transduce by putting the word embeddings as input, and we just get all the output of this RNN. And because we want to use the last hidden state for the classification, so which one? That is, yeah. So we just get the last state of the forward RNN and the last state of the backward RNN, and then we concatenate them together as the final vectors we use for the classification. So here is the training part, which is the same as the previous class.
Okay. So I think that was simple. Are there any questions about that? No? Okay. It's simple, but it's a pretty reasonable baseline if you want to do some sort of classification. So I'll move on to the next one. So RNNs have some problems, and specifically in the sentiment classification task that I was talking about before, or that we just showed before, they suffer from the problem of vanishing gradients. So basically the idea is that every time we run through a RNN step, we are going to be having the gradient decrease. So if we have some sort of loss function at the end, in this case I'm talking about squared error, but we could also have something else. Every time we take a step back, the gradient gets a little smaller, or the gradient changes a little bit. And there's a couple reasons why this happens. One is because if we're using a nonlinearity like the tan H, basically the tan H looks something like this, and then the gradient looks something like this. So anytime we get an input that's not very close to 0, we get our gradient decrease. Or actually so every time we get an input that's not close to 0, the gradient decreases. And if we do this over many, many time steps, we basically lose all our learning signal by the time we get far back. So in this case, we used a bidirectional RNN in our training. So the forward RNN will remember words from the end of the sentence. The backward RNN will remember words from the beginning of the sentence, but the words in the middle of the sentence might be lost due to this vanishing gradient problem. So a solution to this is long short-term memory, LSTM. This is something that a lot of people use, and the basic idea of this is that we want an additive connection between time steps. So we want a connection between time steps that doesn't change the gradient at all. And addition is an operation that doesn't modify the gradient. So you know d of x plus y with respect to x is, sorry, that's not a good example. D of this shows why you should put things on your slide before you start doing them, so you don't come up with mistakes. What should it be? D of fx? Yeah, so d of fx plus y is equal to d of fx. What's that?
F of x plus g of x?
F of x plus g of x, yeah. That's probably right. There we go. So then basically the derivative of this will be unchanged, or will not get smaller based on taking the differentiation here. But anyway, so I'll try to clarify that a little bit better next time. But so if we take a look at what this looks like here, which I can probably use to make that explanation a bit better. We have our xt, so xt is our input. ht minus 1 is our hidden state of the previous time, and ct minus 1 is something called the cell state. So ht minus 1 is what we normally have in our recurrent neural network. So it is like what we normally have in our recurrent neural network, and the C is kind of something special for LSTMs. And the idea is that within every LSTM update, we have this function. And the most important thing is kind of the C across the top it's adding in information, but it's not multiplying by anything. It's not taking any nonlinearity. So this C of t minus 1 the gradient with respect to C of t will be constant. or it will not change due to this operation here. So that's the reason why that's good is because now our gradient will not be disappearing as we pass it along multiple time steps. So this C is basically what the core of the LSTM. Then the H here is also used to do things like modify, modulate gates, decide how much we update C according to something else with new information, etc. So we have a bunch of gates. One is the update gate, which is what value do we want to try to add to the memory cell. The input gate is how much of the update do we want to allow to go through and update the memory cell. So if the input gate is mostly 0, then we won't be updating the memory cell at all. And then the output O is how much of the memory cell do we reflect in the next state. So if the output gate is 0, basically the hidden state will be 0 next time. So there, I can't go through all of the details here, but the most important thing here is that we have this additive connection between the cells, which allows us to avoid the vanishing gradient problem. And then there's other alternatives. So, oh, I'm sorry, this reference is wrong. What I wanted to reference was a paper called LSTM, a search space odyssey. So LSTM, the search space odyssey, is this paper where they basically tried 20 to 30 different variants of the LSTM. And they found that the original LSTM was actually really good. So you can use the original LSTM without being worried too much. Another variant they came up with there is one where you basically set something called the forget gate, which actually wasn't in my previous slide. But you set that to the input gate minus 1, or 1 minus input gate. There's also something called gated recurrent units. These are kind of like a lighter weight variant of the LSTM that everybody uses, that a lot of people use. They tend to have fewer parameters than the LSTM and tend to be a little bit worse, but not a whole lot worse in general. For some tasks, they're about the same. For some tasks, they're a little bit worse. But and they all kind of follow the basic paradigm of taking input, updating the state, etc. So I have some code examples here. I don't actually know if the sentiment LSTM is worth doing because you literally change 2 lines to change the simple RNN into that. And I actually already kind of showed you the LM code. So maybe we can just skip the explanation of these ones and move on. But you can take a look. You can take a look online. So there's a few things that we would like to talk about. Efficiency and memory tricks. So one of the things I talked about at the very beginning is that mini batching is very, very important. Mini batching is a way to make your models train quickly. It was easy to do in feed-forward networks because in feed-forward networks, we're always doing the same computation, and none of the computations over time steps rely on each other. It actually becomes harder in RNNs, significantly harder in RNNs, and there's a reason for this, and the reason why is because each word depends on the previous word. And that sequences are of various length. So here's an example. We have these 2 sequences, and what we would like to do is we would like to basically mini-batch them together. So the way we do this is by grouping together all the words at each of the positions in the sentence and calculating them at the same time. So the way we do this is we basically calculate we add padding to the end of the sentence, the second sentence, because it's a shorter sentence. So we add the end of sentence symbol 1 more time. Then we do whatever loss calculation we want to do. We do a for loop through the entire sentence to calculate the language model. And now after we did padding, all of the sentences will be the same length. So we can just run a for loop over them. Then we have a thing called masking. So what we do in masking is basically all of the padded values, we multiply them by 1 or 0, depending on whether it's a real word or a padded word. And then after we do this masking, we'll basically have losses for all of the non-padded, non-masked ones and no loss for the masked one. And then we take the sum of all of these together. So this is a bit more difficult, but it's really, really important if you want to make models like language models or translation models fast enough that you can actually train them in reasonable time. So this is something that is important to remember. As I mentioned at the beginning, DyNet has automatic mini batching. So one way to do this is to not worry about this and just run multiple sentences at one time and then turn on this flag. But our experiments have shown that that's a little bit slower than doing it manually yourself. So if you want to get the best speed increases, it's probably worth being able to do this. When you're doing mini batching, one of the problems is you don't want to do too much padding. Sorry, that says padding and sorting, but it should be padding and masking. I apologize, I miswrote there. And this results in decreased performance speed-wise. So if you are padding sentences a whole lot, you're going to be doing lots of wasted computation on these padded things, which is not useful. So to remedy this, one thing we often do is we sort sentences before we start training. So sentences of similar length get to be in the same batch, and then this speeds up training quite a bit. So we have an example. This one is probably worth looking at. So I'll again pass this over to Max.
Okay, so this is the code for to show how could we do the mini batching in DyNet. So manually, not in DyNet, just manually. So here is the same. We just read the data, and the only difference is here. Yeah, it's how could we calculate the loss score in a batching way. So let's see where is the code. Here is how could we do batching, how could we do the padding. So first we go through, remember that for the sentence of the input, all the sentences are in decreasing order with respect to their length. So the sentence 0 is the longest one. So for this mini batch, the length of the mini batch is the length of the first sentence. So we just go through the length of the first sentence and to see if, for each sentence, we see if they are shorter than the first sentence. If they are shorter, then we just paddling the end of sentence label to the end of this sentence. And for mask, if it is the real word, then it is 1. If it is the fake word, if it is a paddling word, then it is 0. Then how do we calculate the loss? Here. So basically we just go through every time step. Since we have to process multiple sentences at the same time, so we need to use the affine transfer, which is the a general operation of basically the basic operation of the LSTMs step. And so the only trick is here. So because the sentence is in decreasing order, so we only need to check if the last sentence needs to do the mask. So if the last sentence mask is not there, it's not 1, it means that we need to do the mask. If the last one is still in the valid word, then we do not need to do the mask. So it can save some time. Then yeah, that's the only thing we need to do. Here, So here we need to use the lookup batch version of the lookup. So when you do the lookup, you need to use the batch version of the DyNet operation. So that's the only thing.
So, yeah, just to summarize, you can see it's a little bit more complicated. Another thing that we didn't exactly cover is that here we have some boilerplate code to split things into batches. So you need to split things into batches beforehand, and you need to step over and consider the mini batch size when you're doing your reporting and stuff like that. But you can take a look at this in detail if you're interested later.
So why do we do the longer sentence first?
Oh, so this is the reason why the longest sentence is first is I mentioned before that we're doing sorting. So if you see here, for the training data and the testing data, we do sorting in decreasing order of length. And that way, sentences that are about the same length will be in the same place in the list, so they'll be in the similar places in the mini batch. Yeah. Okay. So that is the mini batching part, and I will move back to the slides. Okay. So, okay. One other thing is about handling long sequences. So if we have let's say we have an extremely long sequence where we want to model. Oh, sorry. Go ahead.
Maybe this is a minor thing.
Yeah.
So I think the order of training data affects the performance.
Oh, right.
So like if you sort the training data by length, then how much does it
It can have an effect. So one thing I should mention is after you made the mini batches, you always shuffle the order of the mini batches that you process. So because of that, in each mini batch, things will all be the same length, and that does have an effect. That can have an effect of making it move very far in the direction of very short sentences in one single mini batch update, or move very far in the direction of long sentences in one mini batch update. But other than that, outside of the mini batch, you're shuffling, so you can reduce that effect to some extent. Yeah.
Another question
Yeah.
is if you sort first,
Mhm.
then isn't the performance of the trained model correlated with the length of an input data?
Hopefully not. Because you're shuffling the mini batches, that shouldn't have a huge effect. Although it does have some effect, but it does make your training a lot faster also. Okay, cool. So I will skip to, or I'll go to the next part. So sometimes you want to handle really long sequences with recurrent neural networks, and this is great, right? Recurrent neural networks can remember things forever. So if you wanted to handle a sequence of 10,000 words, theoretically you would be able to remember something that happened 10,000 words ago, pass it all the way on, and use it in your next prediction of something. So you could do that for, like, let's say you wanted to do a generation of a novel. Like you wanted to create a language model for a novel. It might be useful to do that. Or words in full documents, for example. However, the problem is that this might not fit in memory. It will often not fit in GPU memory. It might not fit in CPU memory either. So there's something called truncated backpropagation through time. And this is a way to basically handle long sequences without actually overflowing your memory. And the idea is relatively simple. Basically what we do is we calculate a whole first sentence like this. We do backprop on the loss function for the first sentence. But then we basically remember this last state. We maybe save it on the CPU or something like that. Then we clear all our GPU memory and delete everything. And then we do our second sentence like this with only the state. So the thing here is that we don't do backprop across the sentences, but we can still use the information from the previous sentences. change our predictions of the next sentence. You might want to do truncated backpropagation through time over 2 sentences, or another way that people often do it is you do it for 40 words, regardless of sentence boundaries. So you just take 40-word blocks and then step through your entire corpus and do it. So this is one way to, basically say we want to do something across sentence boundaries, but we can't hold the entire training corpus in our memory. In order to do the gradients, it's maybe technically possible, but it's difficult because what you need to do is you need to basically throw out your computation graph so you can use that memory. So once you've thrown out the computation graph, you basically have to recalculate it in order to do backpropagation through it. So, so that's the thing I was talking about. That's a little bit more complicated. There's other interesting things you can do, like if you really want to try hard, or you're implementing a neural network library that you really want to be able to do this automatically, there's things like moving some of the intermediate nodes from GPU memory to CPU memory, or from GPU memory to disk, and saving them. That sounds like a lot of work to me, though. So I think this is a more common solution that people use. Okay, so this is something interesting that has a couple interesting results recently, and is important when you want to use RNNs for tasks that they're not particularly good at. So RNNs, particularly deep RNNs or LSTMs, are quite powerful and flexible. Up until about last year, I would say they were by far the most powerful and flexible architecture that we could use. Recently, people have been getting very good results with convolutional networks and stuff, so it's not so clear anymore. But still, I think a lot of the kind of cutting edge results are coming from RNNs. But the difficulty is that these require a lot of data to train them properly. And they also have trouble with weak error signals that are passed back from the end of the sentence, like I said. So like sentence classification, for example, is not, often RNNs will do worse than CNNs, not because they don't have the power to express the sentence, but just because they're more difficult to train. And that's true even if you have LSTMs, sorry.
But are there cases that you step on top of RNN in these convolutions?
So there's lots of ways you could solve this. You could also put attention on top of an RNN, convolution on top of an RNN. And that might be a better solution than what I'm about to talk about, but let me introduce this here, and I think this is interesting in itself. And also, this doesn't add parameters to your model; it doesn't add complexity. Okay, so the idea here is basically training RNNs with weak error signals is difficult. So what we want to do is we want to train them in advance with a non-weak error signal that RNNs are very good at learning from, and so you train for one task and solve another. And the pre-training task is big data and easy to learn. The main task is small data and harder to learn. And we can think of lots and lots of situations where this is the case. One very kind of stereotypical example of this is language modeling and then a sentence classifier. So language models have lots of data. They have so much data that we can't use all of it because the data we can use to train a language model is basically the entire internet in that language. It's also an easy to learn objective because you're predicting the next word, and predicting the next word means the gradients only have to flow back one step before you do an update. Sentence classification, you have few data, and it's a hard to learn objective because you have to pass all the way back through the sentence. So the idea is very simple. We train a big language model first, and then we do sentence classification. And the results here showed that this resulted in much better classifications, which were competitive or better than CNN-based methods. So the idea is learn to predict language and then use that to classify something. This title of why pre-training is maybe not entirely accurate. So why does why does pre-training work on a kind of fine-grained level? So this is a nice paper on visualizing RNNs. It might be difficult to see on the slides here, but you can probably look in the references or on the slides that are online. But basically, this is a visualization of the hidden state of an LSTM after it was learned to predict the next character in either English or source code. So we have one English language model or one source code language model. And basically blue is low and red is high, I think. So then if we look at the cell state for each character, we can see that the one on the top left, this is a single LSTM cell. We can see that it tends to decrease as we step through the sentence. So this is interesting. We have one cell that is basically learning to figure out when we're approaching the end of the sentence. We have another example from English. This is a cell that turns on inside quotes. So the moment you see a quote, basically the cell turns red, turns on. It steps through the entire sentence, and then when it sees another quote, it stops. It turns off. So this is interesting. Maybe it's detecting things like, what people tend to say. So if we have a novel, what's an example of something that would appear within a quote? Any ideas? Wait, what's that? Yeah, direct speech. That's one example. I can think of a very simple example. The word "I" would probably appear in a quote, but the word "I" would not appear in a third-person narrated novel. So there's lots of kind of things that you could think about like this. There is, for the source code one, there's one that turns on inside if statements. Then there are also, one thing I like about this paper is it didn't just take the nice examples, it also took a bunch of other examples that don't really have any intuitive explanation at all. So you can see that a lot of these cells, they don't really mean anything that we can interpret, but they're probably expressing something. It's just we can't really tell what. There are lots of other examples of this, of how these are useful. So the paper on the left by Shi et al. This is a paper where they took, it's not a language model, it's a translation model, but they also tested language models, where they trained this model to do something like language modeling or translation modeling that had nothing to do with parsing, for example. And then they used it, they froze the parameters of the model, then they used this to predict part of speech tags or the aspect or the tense of the sentence. And they were actually able to do it with pretty high accuracy. They were able to do it with much higher accuracy when it was trained as a translation model, but even when it was a language model, they were still able to do so. So that's kind of interesting. You're training it as a language model, but it's learning other things as well. The last one is also interesting. This is training a language model and then using it for sentiment analysis. So they trained a language model on lots and lots of Amazon reviews, and then they used this to predict the sentiment of the sentence. So there's also other examples of stuff like this, but basically pre-training these things is interesting. Okay, so this is actually a little bit early, but I'll finish up here. I'm happy to take any questions. I'm also happy to talk about other things if there's any. Yeah.
On the readings, so how much does the temperature of the gate activation affect the backpropagation of errors?
How does the what of the activation?
So basically the output of the gate is like this linear combination of the gate output. And if the softmax has a very high temperature, it will tend to be just one output and the other. But if it has a lower temperature, it will be more of a linear combination. So how does that temperature affect the LSTM?
I'm not sure. So there's no softmax in an LSTM. Are you talking about the sigmoid function? Or?
The sigmoid function
Okay.
to G.
Well, normally we don't adjust the temperature of the sigmoid function, I think. Usually we just use 1. Are you talking about these like I and O down here?
So it's easier to see in GRUs because it's like 1 minus G plus G.
Okay. So 1 minus G plus G, that's the gating function, and there's no temperature, right? This is the gating function that is based on like the predicted value for the gate. So that's not a parameter. That's a thing that's predicted by the model. Anything else? Yeah. Oh, so the vanishing gradient problem is solved because this cell state is additive, and additive functions do not have any tan h in them to reduce the gradient when you're that close to 0. They don't have any multiplication, and if multiplication by a matrix will either explode or reduce based on whether the values are increasing or decreasing. So that's the main idea. Basically, this is the C is more or less constant minus an additive factor over the time space.
Is it the C that ensures that there is enough long range information on the line?
Yes, basically. So actually, all of the visualizations that I showed you are of the LSTM cell state, the C value. And the C value is the one that's really interesting and learns interesting stuff. The H value, there's a bunch of other things going on there, so it's not nearly as consistent as the C value here. But if you look at if you visualize the C values in the LSTM, you can actually get very nice kind of interpretable stuff. Yeah.
What do you do about shuffling if your dataset size is so large that even because you have to generate a
You mean sorting for mini batches or shuffling? So one way you can do it is just read a subset of the data in and do whatever you would do on the whole data on that subset. So I think a lot of like neural machine translation implementations I know will read in 10,000 sentences and then shuffle those, and then they'll read in another 10,000 sentences and shuffle those or something. You might want to shuffle your whole corpus beforehand using the shuff command on Unix, and the shuff command on Unix shuffles on disk, so you won't have any trouble with that.
Is there any other way for generating a sentence for other than the language model? Because language model, you have to do that either left to right or right to left.
So I think anything that can generate a sentence according to a probability is a language model. By my definition. So a language model is something that calculates the probability of the sentence X. There might be language models that would be very difficult to generate from. So then I guess there are other ways to generate sentences from probability models. So one example is the EMNLP paper I talked about. We might talk about it later in class, but if you want to look it up, it's called Decoding as Continuous Optimization for Neural Machine Translation. And the idea there is that instead of decoding from left to right or right to left, they decode in continuous space and try to generate the whole sentence at once. But I think 99.99% of the time you're not going to do that because it's way harder and way slower, and decoding left to right works pretty well, especially in combination with something like beam search.
So is there anybody try to generate in a tree shape or something?
Oh, there are language models like that. Like there's a model called Recurrent Neural Network Grammars, which is a grammar that generates a tree and the sentence simultaneously. That also is left to right, though. It's just left to right generating a tree structure at the same time. So you might be able to do something more tricky if you want.
I think I have seen that the RNN does not work where if we have the sequence longer than maybe 400 or more.
Okay.
So why does that happen?
It depends where you get your error signal. So when you say work well, it depends on what you're trying to do, maybe. So if you're trying to do document classification with an RNN over a sequence of 400, that's because it's hard for it to pass the gradient back and find the best place. It has to do, 400 time steps back through time. And even LSTMs, once you get that far, they stop working as well as you would like them to. If you have another application like language modeling, it should be able to work relatively well, but it might not catch the really long distance dependencies, I guess.
You mean that in any case it's because of the gradient vanishing problem?
Yeah, you can call it the gradient vanishing problem. You can also call it a problem, there's another term called credit assignment, which is which word was responsible for the decision. And if you have 400 words, it's really hard to decide which one was the one that actually made the difference, right? And it's harder in these more complicated things that have to pass things a long time. So, yeah. Okay. If there's nothing else, it's a little bit early, but I'll end now. And if there's any other questions, I'd be happy to answer. Thanks.